is that, so now we have know the benefit of Laplace transform. We can go entirely analogously to discrete time signals. In discrete time system, we talked about models in discrete time in dt are something that looks like this. So yk plus, let's say, b yk minus 1 equal to a uk. In the discrete time, there are these discrete time instances where we analyze the dependence, the relationship between the input and output. This is easy enough to solve, actually. But if I have a lot of terms in this model, then the solution becomes not so easy. This is ordinary difference equation. Capital O, little d, capital E. We can usually reasonably enough to solve lower order systems. But if the order is high, then it's going to be tedious to obtain the time solution. Now, Z transform is doing the same thing as the Laplace transform here. It's going to transform the ordinary difference equation to some property in the Z domain, so-called Z domain. So it's still algebraic equation, which is easy to manipulate in the Z domain. And then we can use inverse transform, inverse Z transform to go back to the time domain. That is the big picture. Some terminologies, and then we're going to talk about how it is defined, what kind of property it must satisfy, and then give you some examples. Now, this is a discrete time sequence. All these are discrete time sequences that are defined at discrete intervals, time intervals. So we talked about the big picture and why it's a powerful tool to solve ordinary differential equations, and then the analogy between Z domain and S domain. Z domain, the main tools, Laplace transform, we talk about the pioneers who did contribute significantly to Laplace transform. These are in the early days, right? It's in the 17th century. Now, Z transform is one of the techniques that happened in the last century. Z domain, the Z transform, the pioneers, of course, Laplace is still a main pioneer. Because of his Laplace transform, people started thinking about Z transform. It became known, the Z transform technique became known when radar system becomes available. So this is in the World War time. A lot of radar systems. And over there, we have this so-called sampled data system where you have discrete, the system is discrete intrinsically. And then people started using this technique to analyze those systems. It is known from sampled data control system in radar applications. The name Z transform comes from one of the pioneers who worked a lot on Z transform in the early days. The name is actually adopted from two professors in it's Ragazzini and Dader. These two professors, they are at Columbia University in New York. They called this kind of technique called Z transform started using that in 1952. So that's relatively recent compared to Newton's age, right? This is in Columbia University. And then I guess they had a student who also worked on this. And the student continued to work on this after he graduated and worked in a university as a professor himself. Another important pioneer, so the advanced Z transform is done a lot by a professor named Guri, G-U-R-I. So this is a professor. He graduated from Columbia University in 1953-ish, and then he started working at UC Berkeley and University of Miami. So he's still actually alive today. So this is one of the techniques that is relatively recent. And his papers, he has a lot of papers that I still, when I was doing my PhD, I read that papers a lot. So a lot of nice results from there. Now, let's quickly talk about the definition. Let's actually take a break and then come back in about 2 or 3 minutes. It is because the sequence is discrete, so the notion of integration over a discrete sequence is not sound. We have summation instead. It is summation of the sequence times also some term that has a power element inside. This is e to the power of negative st, then this is z to the power of negative k, and we are summing over k. This is going from 0 to infinity for the sequence. So if you can write it out, is when k is 0, you're going to get f of 0 when k is 0 is x of 0 times z to the power of negative 0. That's 1. And then when k is 1, it's x of 1 times z to the power of negative 1, x2, z to the power of negative 2, etc. And this z is similar as s in the s domain, so they are both complex numbers. The same as Laplace transform, because this is just a summing up or multiplying the time domain signals by some terms. So it's a linear combination of the time sequence x. And because of that, it is a linear operator. So it satisfies the superposition principle. You can replace x of k by, let's say, alpha times fk plus beta times gk. Then this term doesn't change at all, and the summation doesn't change. So it's going to be the linear combination of the z transform of f and g. So that gives us immediately a good impression. This is a nice definition. It has good properties. Similar to integration, when we talk about something that happens at infinity, when we are summing up, adding up things to infinity, it's important to consider whether this sum actually converges to anything. So there's this notion that it actually will converge under some region of convergence. Take a look. We know from calculus that if I have 1 minus x, 1 plus x is 1 minus x squared. If we have 1 minus x, 1 plus x squared is 1 minus x to the power of 3. If you keep adding terms to here, then you're going to get 1 minus x to a power of whatever, how many terms over here. And if your x is less than 1, you are taking powers of some number that's less than 1, then it's going to go to infinity. It's going to go to 0, right? So if it's 0.1 to the power of 100, it's a small number. So that's the region of convergence. That's the notion of region of convergence. This series, 1 plus x plus x2, and then adding up all the way to infinity, will converge to just divide both sides by 1 minus x. This series will converge to 1 over 1 minus x if the magnitude of x is less than 1. This is just another way of writing this down. If you sum something up from 0 to power of n, then it's going to be 1 minus beta n plus 1 divided by 1 minus beta, if beta is not 1. From this result, we can immediately get many Z-transform pairs, such as these two over here. First is a geometric sequence. It looks like, so let's say A is less than 1. So it's going to be A is going to be 1, and then A is less than 1 when K is 1. It's going to be here, and then it keeps reducing to 0. So it's a geometric sequence. We can compute the Z-transform of this very easily. So by definition, we have summation 0 to infinity, A times K Z to the power of negative K. And you can see the two terms, I can combine them to AZ negative 1 K. So consider this as a new, let's say, x. Then it's just going to be 1 plus x squared, x to the power of 3, etc. From the convergent analysis from the last slide, it's going to be 1 over 1 minus a z negative 1. This is one of the fundamental Z-transform pair. If f of k is ak, then f of z is 1 over 1 minus a z negative 1. We can make it, we can use it, use a different form. We can multiply z both in the numerator and denominator and get its equivalent form, z over z minus a. So the region of convergence is that for this to converge to this, we talked about this a, this element x here, the magnitude must be less than 1, which is the same as z magnitude should be larger than a. From here, we can quickly get the Z-transform of a step function, for example. The unit step in discrete time is like this. It's always constant 1 for all time. So the sequence itself doesn't converge to 0, but it still has a Z-transform. And it's just a special case for A being equal to what? 1, right? It's just a special case here, so we can use this formula quickly to obtain the z transform of a step signal is 1 over 1 minus z to the power of negative 1, or z divided by z minus 1. The region of convergence is this z must be larger than 1, so it's just letting a to be 1, and it's going to be here. Now we talked about a continuous time impulse. In discrete time, there's discrete time impulse that looks like this time it's slightly different. In continuous time, an impulse has infinite magnitude. In discrete time, it has a unit magnitude of 1, and then it's 0 otherwise. So it's like this. The z transform is, by definition, quite easy. It's 1. You can see this by writing out k from 0 to infinity, delta k, z negative k. So it's delta 0 times 1 plus delta 1 times z negative 1, etc. Now because the value is 0 for k equal to 1, 2, 3, etc., so it just has the first term remaining. So it's delta 0, which is 1. So the definition of these two impulse functions are different. However, the Laplace transform and z transform of them are the same. So impulse gives you 1 in the transform domain. Now we talked about how to obtain Laplace of sine and cosine functions. Let's do an exercise about the z transform of sine and cosine. There's a question? Let's say this is the sequence that we're talking about. This is a discrete time sequence. It has value only when for these specific locations in time. And then we are doing summations. Let's call this x of k. Now your classmate is saying, hey, if I consider this function as sort of a continuous time function that looks like this, its value at these time instances are whatever the circles over here, and in between it's 0. So I wish I had a red pen. Let me try. So then, if we consider the Laplace transform of this seemingly continuous time function, let's say 0 to infinity, let me call this x tilde t e negative st dt. This x tilde of t only has value, like in these instances, it's all 0 in between. This is actually picking out, it's doing something similar in this definition, right? Do you guys see that? That's actually a good intuition. You can regard this by some intuition from here. Now, what is the only difference? What is the only thing that we see different in the definitions?
Discrete time is simply time, but time period, simply time period.
So that's going, you're going a little bit too far beyond. We haven't talked about those things, but I understand what you're saying. So you're saying different continuous time signals after sampling can give you same discrete time signal.
So they're not the same, you cannot convert to each other.
So I hear you. We're going to talk about sampling later, but I see your point. Now, what I was asking in these two definitions is, what is the difference here? What I was trying to hint you guys, here I have e negative st, and here is z, right? So that's the difference in notation. Now, we will actually go to discuss how to interpret Z and S. They are actually connected, but that will happen when we talk about sampling discrete time signals. That's a good observation. So Z is actually related to E as something in the future. That's good. It's good observations. Now, let's go back to, we finished carrying out the Z transform of impulse. Let's work on this one, is cosine functions. We can use definitions for sure, and the way I want to go today is to use the Euler equation of cosine omega 0k equal to, cosine is just a sine, it's just exponential functions in alternative form. Cosine omega k is half of e to the power of j omega k plus e to the power of negative j omega k divided by 2. And we talked about this one, right? AK corresponds to 1 divided by 1 minus 8z. So as a special case, if I have e j omega 0k, this e j omega 0 is my A. So is Z transform is EY minus EJ omega 0 Z inverse. So this is just a special case of the geometric sequence. And if it's negative, you get a negative here. I know the Z transform of this one and this one. So this corresponds to 1 over 1 minus EJ omega 0 Z inverse. And this is 1 over E negative J omega 0 Z inverse. These are just manipulation of algebraic equations in the Z domain, right? Addition, multiplication, easy. Is 1 minus EJ omega 0, Z negative 1, 1 minus E negative J omega 0, Z minus 1. In the numerator, so this is plus. In the numerator, for the first term, is 1 minus E negative J omega Z minus 1. And then add 1 minus E J omega Z minus 1. This one looks a little bit, starting from here, you see it's a little bit different from Laplace transform. But the result, actually, the simplification we will be doing is very similar. It's just using the properties of, it's using Euler equation back and forth. I have in the numerator 2 minus a common term Z negative 1 times E j omega 0 plus E negative j omega 0. Actually do this. And in the denominator, we have 1 minus E negative j omega 0 Z minus 1 minus E j omega 0 Z minus 1 times 1. And then this times this. So it's plus E j omega 0 times E negative j omega 0 cancels out. Z minus 1 times Z minus 1 is Z minus 2. Technically, we have written out, so this function, if you look at it, is a function of Z. It's not a function of K. anymore, right? Technically, we have obtained the Z transform. We can simplify this just a little bit further, but this is, by observation, this is now in the Z domain. It's no longer in the time domain. So we can simplify this a little bit more by noting, let's start from the numerator. In the numerator, what do we have here? 2 minus Z negative 1. What is E j omega 0 plus E negative j omega 0? 2 cosine omega 0 j, there's no j. That's it. What is in the denominator? I'm going to have E minus 1 minus Z negative 1. What do we have here? E negative j omega 0 plus E j omega 0, which is another 2 cosine omega 0. And then Z to the power of negative 2. Don't forget, we have a 1 division by 2 left over. So overall, the Z transform of cosine omega 0 k is division by 2, cancels out this one and this one. It's 1 minus Z negative 1 cosine 1 minus Z negative 1 twice cosine. So that is the final formula for Z transform of cosine signal. Now let's take a look at the formula and build some insights into it. In the S domain, cosine omega t is what? A second order function of S. So it's right here. I got sine, but you can we talked about cosine. Cosine is going to be S over S squared plus omega squared. The result here is telling us in the discrete time case, if you have discrete cosine sequence, it is also a second order function of Z in the Z domain. Any questions for this exercise?
Where did the 2 go?
So the 2 went away. So we talked about this is the Laplace transform of this, the Z transform of this one. So this was left out at this step. And then I bring it back to here. So we talked about the Z transform is a linear operation. Similarly to Laplace transform, it's going to possess very nice properties that will be convenient for system analysis. So we're going to talk about a few of them and then present a few more Z transform pairs that look like these. So let's take a look at, so in the time domain, we have continuous time domain. We have differentiation corresponds to S multiplying f of s, and derivative is division by s. Integration in the time domain is division by s in the s domain, right? Here, because we no longer have the concept of derivative in the discrete time sequence, we can't take derivative of the sequence at this time. What we do is actually, we can still look forward and backward, just like taking differentiations. We can look backward and tell what the Z transform of a shifted sequence look like. We can also go forward and take a look at Z transform of a forward shifted sequence looks like. So let's talk about this one-step delay. It happens all the time. The new sequence, if I have an original sequence X that has a Z transform capital X Z, that looks like this. So we can construct a delayed version of this sequence. Then the Z transform is, by definition, is summation from 0 to infinity x, the sequence x times z to the power of negative k. So it looks a little bit different from our standard definition, but what we can do is construct something that will look like so. The main goal is to, from here, be able to construct something that looks like this eventually. We can take a look at the result here. If the summation is from 0 to infinity, what is the first value of x that I need to take a look at? It's x minus 1, right? And I have one more element that I don't need. I should be looking at the sequence from k at 0. So I take out this additional element and consider the summation from 1 to infinity. Now, because this summation from 1 to infinity is essentially letting us to go from, this k minus 1 is going from 0 to infinity, right? The only thing that, now we have almost everything. We have this part figured out. We just need to create this term. So that's how we do it. I see that the index is k minus 1, k from 1 to infinity. I just create a similar index in the z. I created the index k minus 1 here, so it's z to the power of negative k minus 1. So I have an extra z inside. So to make these two match, I have to multiply this by z to the power of negative 1. It's just a different way of representing the same thing. But because this summation is for k, so z is a scalar, I can easily pull this outside. And then inside, I have essentially summation k from 1 to infinity x k minus 1 z negative k minus 1, right? This is equal. So therefore, if I take this out to here, this is z minus 1, z to the power of negative 1 times capital X of z. And then we are done. So there's an additional x minus 1 term. And under this assumption that I only take a look at signals that is 0 if time is negative, this is 0. The one-step delay, the z transform, is z to the power of negative 1 times x of z, capital X of z. All right, why don't you guys work on this one? Very similar techniques. For one-step advance, if the sequence is shifted one more step in advance, what will be the z transform?
Sorry, could you explain again why x of negative 1 goes away?
Yes. So in continuous time signals, we made the assumption that we are only looking at signals that has value in when time is positive, right? Because my integration is this. It's starting from 0. So in the discrete time, because we are defining the z transform of k from 0 to infinity, the assumption that we make is the signal is 0 for negative time. When we have signals, when we have systems that look like this, xk plus 1 equal to ak plus bk, and we assume the initial conditions are 0, then I can use these formulas. Is the z transform of a one-step advanced signal is z times x of z, and then minus the initial condition. If it's initial condition 0, then it's 0. So on the right is just a standard z transform. X corresponding to capital XZ, U corresponding to capital UZ. So it's very similar to Laplace transform. Then we're going to have, we can combine the term about x. So it's z times constant. So suppose these are matrices. These are all vectors. Then A is going to be a matrix. And B is going to be a vector as well. Suppose this is the model. We can do z minus A, combine the term about x, and then do the inverse. So this is going from z minus A, x of z equal to b u of z. These are matrices. If I can invert these matrices, then this will be the z transform of xz from here. This is something that we will be using in system analysis. So it turns out this is a very common model for dynamical systems. Let's use the technique to solve a difference equation. The output depends on the input. It doesn't directly depend on the input at time k. It depends on the input applied in the 2 steps ahead. So after the input is applied to the system, there are some delays, and what I can impact is something in the future. So that's this k and k minus 2. So the output also depends on like the output in the past as well. So we have yk dependent on the previous outputs and the inputs 2 steps back. So we can solve this difference equation very quickly using the transform techniques. So similar to continuous time systems, we're just going to do Laplace in continuous time and do z transform in discrete time. So remember what I just talked about. I would like to give you this concept. I talked about if I'm considering the z transform of a delayed sequence, we did 1 step delay in the past, is we need to add or subtract 1 term. Now, if it's 2 steps delay, then you see is adding 2 additional terms. That's the result. And the individual steps is actually just repeatedly using the formula we did last time. The formula that we did is we know how to compute, if I denote this as k prime, then we know how to compute a 1-step delayed sequence, the z transform, right? We can regard this one as a new time index. So I know how yk prime minus 1, the z transform looks like. So it's going to be the z negative 1. This is a new index. For k prime, this is just delayed by 1 step. Therefore, the z transform is z minus 1, the z transform of this yk prime signal. Then plus yk prime equal to negative 1. Right? So just using this formula here. Treat yk prime as a new sequence here. And then apply this formula once, we get this. And then apply the formula for a second time to derive the z transform of 1-step delayed sequence yk minus 1, which is z negative 1y plus 1 negative 1. This is how rigorously we should be writing things out. Now, in practice, here's the good news. Although this looks a little bit tedious, but in practice, remember what we talked about. We are only concerned with signals that are negative that are 0 when time is negative. So for all these sequences, we talk about y minus 1, y minus 2 is 0. In practice, these are going to go away. We usually don't need to worry about them too much unless specifically the problem asks you to do so. In practice, the good news is that we can just write z transform of two-step delay is going to be z negative 2 yz. Easy enough. So that's the good news. But rigorously, this is the underlying procedures. So therefore, doing the z transform here, z transform of yk is yz, z transform of 3 yk minus 1 is 3 z minus 1 times yk, and 2yk minus 2 is 2 times z negative 2 yk. All these initial conditions, they are 0, so we don't need to worry about them. On the right-hand side, we have two-step delay for u. It's going to be z minus 2 uz. And then we can divide things out and make the result explicit to be a relationship between the output and the input. So this is z minus 2 divided by 1 plus 3z negative 2 plus 2z negative 2, and multiply both the numerator and denominator by z squared. So it's going to be z negative 2 times z power of 2 is going to be 1, and then z squared 3 times z plus 2. That is the discrete time transfer function between u and y. Now, we can, from up to this stage, this is just the relationship between u and y. We haven't talked about what is u yet. If u is a step signal, then we can use this transfer function to derive the output very quickly. So if u is a step, what is the z transform? It's using this formula, right? Is a equal to 1. So the step signal, the z transform is right over here. It's 1 over 1 minus z to the power of negative 1. So just plug this to here, we get z minus z plus 2, z plus 1 times uz is z divided by z minus 1. Any questions up to this stage? Now, this is something very similar in the Laplace transform example. We have a third order z function, and we know these fundamental z transform pairs. Some of these terms look very similar, right? Z minus 1, if you think about it, this is corresponding to something that looks like this. And z plus 2 is going to be something related to 1 plus 2 times z minus 1. And then this is 1 plus z minus 1, corresponding to these individual terms. So then we can decompose this large transfer function into smaller elements, each of them with very easy inverse z transform. So that's the big picture. This is another partial fraction expansion, right? So is after we recognize these individual terms that is easy to compute, we are creating the small modules and calculate these coefficients. It's a partial fraction expansion problem. We will be giving you all the details about this partial fraction expansion next time.